then we get C equal to 0. So we have only FV equal to MV. So I can use the total probability equal to 1. Okay, and then you should be able to get the M. Share your answer once you get the M for the second side, side B. Zero 0.005. Okay, so it means that we can get the equation for side B. FB equal to 0.005 V only. Okay, so based on this, we can calculate the wind distribution and the average power based on the same equation over here. Okay, so we get the average power for side B. (1.2 megawatt). Okay, once you have the average power output, then you should be able to calculate the revenue. Times 24 hours, times 365 days, times 20 years. and then it can sell at the price of 60 ringgit per megawatt hour. Then once you get the revenue, you also can calculate the expenses. Expenses, we have the various expenses. Okay, expenses for site B, land 2 million, turbine capital 2 million, O&M 100,000 per year. So for 20 years, another 2 million. So 2 plus 2 plus 2, so we have 6 million of the expenses. However, our revenue is 12.6 million. Okay, so we can get our net profit. And this value is much better than to build at site A. Okay, can follow? Site A and site B. Okay, then I think we can move to the next one. Okay, now we have done the calculation, for example, 4.1. Now we move to the power control. Power control means that you look on the graph over here. Okay, here. Remember that when the speed, you can see that the rated power happened at maybe 11 meter per second of wind speed. But beyond the 11 meter per second, the power output will remain constant. So it means that we try to limit the power output, or we control the power. That's why we call it power control. But how we control the power? Okay, so am I going to apply the brake like a car? You want to make it move slower, so you apply the brake. It won't happen and not really suitable to apply the brake on the wind turbine for these purposes, because this will happen for more than maybe a few hours continuously. What kind of brake can sustain a few hours of the friction? And then the wear and tear for the brake pad and the disc, maybe you want to use this brake, the disc also will be very expensive. So we are not able to use the typical brake system to just slow down the wind turbine rotation speed. Okay, there is a brake in the wind turbine, but not to slow down it, but just to stop it when the power output is too low. But when you have high speed, normally we won't use speed. Sorry, normally we won't use brake, but we use the power control system. Okay, the concept of power control system is actually we change the angle of attack. Remember that the lift force will affected by the angle of attack. So if I change the angle of attack of the wind, So it means that you will get less lift force. You will get less lift force. It means that your turbine will rotate slowly because you get less input from the wind. Okay, so how we do it? We have two methods. We can rotate the angle on the blade. You have the aerofoil shape of the blade, correct? So now I want to change the shape, change the angle, so that the angle of attack will change. Okay, you can see that wind turbine is designed to produce electrical energy as cheaply as possible. Wind turbines are therefore generally designed so that they yield maximum power output at wind speed around 15 meters per second. It does not pay to design turbines that maximize the output at strong wind because such strong wind are rare. Okay, I limit the power output actually is to protect the system, to protect the gearbox, to protect the generator. Okay, but you may ask why you not target on strong wind. You get a bigger generator, you get the better gearbox, then should able to sustain. Yes, definitely you are correct. But bigger generator and better gearbox normally cost you more, and the strong wind is actually very rare. So maybe just happen once a year, but you put in so many money just to target the strong wind once a year. So it's not really worth for the investment. Okay, so normally we will design a smaller size of the generator and gearbox, which target around 50 meters per second. Although the wind speed can up to 20 or 25 meters per second. Okay. In case of strong wind, it's necessary to waste part of the excess energy of the wind in order to avoid damaging the wind turbine. Okay, this damaging refer to the gearbox and the generator lah. Okay, the blade itself, we don't help much in that case. All wind turbines are therefore designed with some sort of power control, and there are two different ways to doing this safely on modern wind turbine, which we call as a stall control or pitch control. Stall control is passive control, and pitch control is an active control. So you know that passive and active. Passive, we do not need energy input. We do not need any feedback. Okay, don't feedback to the system. So we not really target, I'll say at what wind speed, we target what angle. No, that's a passive control. And for pitch control is active control where you need to change angle from time to time. Okay, based on the speed of the wind. So it will be more complicated, but the output will be more accurate because now you are doing direct feedback. Okay, active control system. So first we talk about the pitch control, which is the active control system. Okay, so when the power output become too high, it sends an order to the blade pitch mechanism, which immediately pitch the rotor blade slightly out of the wind. You can see that the blade actually can rotate. Okay, so that the change angle of attack. Okay, something like this. I will go back to the lift and drag. Okay, to refer to this figure, you can see that if I change the angle by attack, it will change the lift force and combination of lift and drag force. Okay, so in other words, I can change the power output from the wind turbine. This is the method lah. Okay. Okay, so how they actually rotate, you can see that the pitch mechanism usually operated by using the hydraulic. And you want to rotate the blade one by one, 3 blades together. Okay, and the rotational and the mechanism actually is quite complicated. Okay, because actually the blade is very heavy. It's not 1 meter, 2 meter. Okay, it can be a 20 meter, 5 meter. Okay, so it's very heavy. You want to rotate this, you need a very good hydraulic system here, big scale hydraulic system and 3. Okay, and together with the input from the wind speed and rotation. Okay, so this is a best control, best power control wind turbine, but of course the cost is more expensive. Okay, so if you look on the power curve of pitch control, it will be like this. Cut in. Okay, cut in is mean that at what speed the wind turbine start to rotate. Okay, of course, below this speed, the wind turbine still able to rotate, but too slow. So whenever it rotates too slow, the power generated is too less. So end up with the wind turbine is not generating power, but actually consume power. The reason is, yes, you may think that, yes, I rotate slow, then I get less output. Yes, fine. But why negative? Because the wind turbine itself will have a lot of control system, including the yawing. You want to change the direction of the wind turbine blade so they keep facing the wind. Okay, so you do that, you need energy to rotate. Okay, and then you need a control system. You need a monitoring system. All is about the energy. You need energy, but of course the main energy comes from the yawing. You change the direction of the wind turbine. Just make sure it faces the wind. But when the wind speed is too low, you spend more power to rotate the blade greater than you generate. So what's the point to do that? So that we apply the brake. Okay, so below this value, below cut-in value, the wind turbine is not allowed to rotate. Just apply the brake, holding it. Okay, so that you won't waste the energy. Okay, so cut-in energy is where it starts to generate extra net power. We call it net power lah, because net power refers to the power generated minus the power consumed. Okay, so this is the value where we start have the generate net power. Okay, and then of course when the wind speed increase, it will in the power output will increase in the log scale power. V power of 3 in the cube of velocity until it reach the rated power at this one, maximum power rated. And after this point, the active stall control will happen. Active stall is mean that pitch control lah. Huh? Okay, so it will start to rotate, change the angle. Okay, okay. What is the best angle? Best angle is you have very high lift force, you have very low drag force. This is the best solution. But in case I already reached the maximum, then I change angle a bit so that the lift force reduce, but the drag force increase. Remember that drag force will not generate any power to the system. Okay, drag force is applied just to bend the blade. It's an unwanted force. But now, no choice. We do not want too much energy input, so that we convert a little bit to the unwanted force. Okay, so here start to have the active stall control. Okay, and then same thing, you will keep changing the angle to maintain the power output. Okay, change the angle effect so that the rated power will maintain at the same power output at different wind speed. Okay, this is to protect the system now. Okay, and up to 25 meter per second of wind speed, we have one called cut out wind speed. Cut out wind speed is mean that I cannot run anymore. My stall control is not able to function well at 25 meters per second of wind speed and above. So in that case, you need to stop your wind turbine from rotating because your pitch control or stall control is not strong enough to reduce the lift force. So in that case, again, you need to stop the turbine from rotating. Then you apply the brake. Apply the brake, stop to 0. The speed must stop to 0. It's different from the brake in our car. We can use the brake to slow down the car. Okay, but this one is just stop the car. But you not used to slow down the wind turbine for long term, but it's just to stop. Okay, so this is a cut out wind speed. Okay, so I think here we have 3 different conditions: cut in, rated, and cut out. And you can see that it will be a straight line. This is because we have the active stall control. We have the hydraulic system to change the angle of attack of the blade. This is the first part. Second one, we call stall control. Stall control is a passive controller. Passive means that I don't need any energy input. And I don't need any feedback control. Sorry. So how I do it? This is very important in terms of wind turbine design. Okay, as I know that maybe you go back to this. Okay, you see, this is the free flow direction, and this is the rotational free speed generated by the rotation. Okay, and angle of attack definitely will be affected by these two speed of fluid. Okay, so that stall control is mean that you need to study the history of the wind flow. Okay, and then you design the wind speed and the angle accurately, so that at high wind speed it will create a stall. Create a stall, I mean it will create the stall to destroy the lift force. But only it will create the stall at the high speed. It won't create the stall at the low speed. This is the design criteria. Okay, how to do that? If you look at here, let's say my rotational turbine blade is consistent, then this fluid speed actually able to change the angle of attack. So if I consider the change in between these two speeds, I'm able to control the angle of attack. So I adjust the angle properly, and then fix it and install. And there's no other control after this. So it means that the turbine blade is fixed over there. Okay, this kind of system is less effective, and it will reduce the efficiency. Okay, why? You can see that cut in and cut out. Sorry, cut in and rated. Okay, so this is a pitch control. We go to this stall control. Cut in and cut out stay the same. But the problem is you can see that it will not change immediately to straight line. You have to change gradually because the speed is changed gradually. So the rated power also will change gradually because it changed the angle effect slowly, not like active stall. It will change immediately to the angle effect that you want. But this one you cannot change because it's passive system. It is fixed angle. Okay, so it won't have the two smooth path. It will be like this. And at the same time, because you change your angle of attack, the efficiency below this rated power will also drop because that is not at the optimum angle of attack, because you have to consider the stall control at the back as well. Okay, so you need to compensate a bit for this system. It will be not so effective, but it's much cheaper because you do not need to install a hydraulic control system on the blade. Okay, so both of them have their advantages and disadvantages. So these are the main two power control system used today. If you want to go for cheap price, then you choose stall control. If you need the higher efficiency, then you can use the pitch control. Okay, but how to choose? So maybe in location that the wind speed change very fast, so maybe you can consider to use a pitch control. But for the location the wind speed quite constant, maybe stall control is good enough. Okay, of course, this one you have to list out for maybe 20 years how much is the power output and what's the revenue for both. Okay, and then the net profit, because the cost is already different, and the maintenance cost for hydraulic system definitely will be more expensive. Okay, we won't say which one is better, but both have their advantages and disadvantages. Depends on what you want, what kind of the requirement you need. Okay, so this one called stall control. Just have a fixed angle. So you can see that at a certain angle, because when the speed increase, the angle by attack will change. So at one moment, the wind speed become too high, it creates turbulence on the side of the rotor blade. This one turbulent, and this actually is a pressure with high. So it is a region with high pressure which destroy the lift force. Okay, but if you put the blade in tension and bending, so your blade must be in the better strength in that case. Okay, we have two types of power control: stall control and pitch control. One is active control, one is a passive control. Okay, you can see that the stall control represents a very complex aerodynamic design problem and a rated design challenge in the structural dynamic of the whole wind turbine, which you want to avoid the stall induced vibration. Because you can see that the back side here we have stall with high pressure. One side, because high speed, you have low pressure. Okay, so if you have a maybe your vibrate. Okay, so you have to control the vibration as well for this kit, because you are not able to control it after you install because passive. Okay, around 2/3 of the wind turbine currently being installed in the world are store control chip. Seem like cheaper price going to win the market. Okay, because we also don't want to maintain the system from time to time. So the store control still have 2/3 of the market share. But the problem is this actually represents very complex aerodynamic design. But the pitch control, yes, the design system is complicated, but in terms of aerodynamic, it's not so complicated because I can change the angle anytime. I don't care. Whichever needed, I change. But this one, once installed, is forever. You cannot change from time to time. Okay. And this is a photo lah. I think captured by the slow motion photo. This is the flow. Okay, the white line represent the flow of air. Okay, maybe I think they make it smoke lah, white smoke, so that you can see the flow of the wind. You can see that there is a separation separation region over here. Here is the high speed, but here suddenly over stationary. The air always almost stationary, and we call it as stop. Okay. Okay. Then after the stop control, we talk about the rotor solidity. How solid is the rotor? This one we call as the rotor solidity. So solidity is the ratio of the total rotor plane form area to the total strap area. Total strap area is the total area here. We are cut by this blade. We call total strap area. So the solidity is the total area covered by the blade over the total strap area. So in that case, for this system, it will be 3 small a over capital A. Okay, capital A is a strap area, and small a is represent the area for one blade. Okay, so normally when you have less number of blades, you have low solidity. Okay, and you have more number of blades, it will be high solidity. And how it affect the result? You can see that when you have a few blade only, the system is very lightweight. Okay, you have 3 blade and lightweight, so it can be rotated at very high speed. But same thing, because of the lightweight, you are not able to generate high torque. So low solidity will have the high speed but low torque. But high solidity will have the low speed but high torque. You can see that this one, they have so many blades. So you can imagine that how much momentum you need to rotate the blade. Okay, so once you rotate the blade, how much momentum you need to stop the blade. I can say that high solidity turbine is difficult to start and difficult to stop. It will move slowly, okay, but very high torque. So they have their different application. Okay, so maybe I can explain this way. Lorry and a car. Do you think the power of the lorry is smaller than the power of your car? Definitely not. The power of the lorry is much bigger and much higher than the power of a small passenger car. But why the speed cannot be go up to certain speed? Cannot be complete with you. You can always bypass, okay, the lorry, but lorry quite difficult to bypass you. The reason is the engine is designed for high torque but low speed. But for the passenger car engine is for high speed and low torque. Okay, so when you have high torque, you will have a very difficulty. You have the difficulty to stop and start. Okay, but good thing is you have the very big torque to move the heavy object. Okay, so in terms of application, low solidity is for high speed application. For example, electricity generation. Okay, why I say so? For example, electricity generation, the current or the AC, alternate current normal use in Malaysia is 50 hertz and or 60 hertz. It means that 50 revolution per second. Okay, So it means that you want to create this alternate current, you need to move as fast as the 50 hertz or 60 hertz. Okay, but actually for the normal wind turbine blade, even three blade, it will rotate at just around 30 to 60 rotational per minute. Okay, much slower than the rotational speed. AC current needed, the frequency for the AC current. Okay, so in general, the AC current require the speed of around 1000 to 2000 RPM of the rotation. So of course, we are not able to achieve with rotational speed of 1000 to 2000 RPM on the blade. So that we need the gearbox. Okay, but gearbox, another problem is the gear ratio. We try to minimize the gear ratio. Okay, so that it will be cheaper and less maintenance. So to minimize the gear ratio, it means that you need to use the high speed system. Okay, the input high so that you don't need to amplify so many to generate more electricity. Okay, in general, I think from 60 RPM to maybe 1008 RPM, there's quite a lot already. Okay, but this high solidity normally is for where you don't need the low high speed and you need torque. For example, pump. Water is very heavy, but do you need to pump it very fast? Not really. I just need a very high torque to move the water. Okay, because water is very heavy. Okay, so high solidity normally for the high torque, for example, pump. Low solidity normally for high speed, which is electricity generation. Okay, so of course, if you see commercial wind turbine, normally you see three blade only. That's definitely for power generation. Of course, in the figure here, bottom, there's a lot of blade one. I think if you go somewhere, they use the wind energy for the pump, then you can see this. Okay, it's normally just for pumping purposes. Okay, and then you can see that this is the solidity and the tip speed ratio. Okay, I mean that the optimum tip speed ratio. You can see that the less number of the less the solidity, the tip speed ratio will be at a higher range. Okay, so it means that you have to move at faster speed to get the best efficiency. Okay. Okay, I think this one I just explained high solidity wind turbine or low solidity wind turbine is suitable for electricity generation. Definitely we need the high solidity, sorry, we need low solidity wind turbine, which rotate faster. Okay. Okay, then we talk about the orientation of the wind turbine. Okay, in general, we have two orientation of the wind turbine, which is the vertical and horizontal. Okay, vertical, which is we always see. Sorry. This is vertical at the right hand side, and horizontal is at the left hand side. You can see the blade is horizontal to the surface of the ground surface. Okay, and this is vertical. Okay, which one you see the most? I think most of us we see the horizontal wind turbine. So it means that horizontal wind turbine is actually more cost effective. Okay, so most of the system design will use a horizontal wind turbine rather than vertical axis wind turbine. Only the small scale wind turbine, for example, if you see at the right hand side, very small scale wind turbine, still possible to use the vertical axis wind turbine. Okay, normally vertical axis wind turbine is quite good in location with the low wind speed, for example, in Malaysia. Okay, but in the where you have strong wind speed, definitely this horizontal wind turbine will be much better. Okay, so now we make a comparison between this vertical and horizontal. Okay, sorry, horizontal and vertical. So we talk about the vertical first. This is vertical. So you can see from here, vertical, what's the advantage? You can see that the blade, it has three blades and all in three different directions. So The good thing is it can accept wind from any angle and direction. Whichever direction the wind come from, it can rotate the turbine blade. Okay, but this one cannot. Horizontal wind turbine, you must always rotate your blade to face to the wind. It only able to accept wind come from the front, come from back, come from the side, no use. Okay, so this is the first advantage of the vertical turbine. It can accept wind from any direction. Secondly, do you notice that the gearbox and the generator all is mounted on the ground? And this one, vertical axis wind turbine, gearbox and generator all is mounted on the nutshell at the top, on the top of tower. So it makes it quite easy to service vertical axis wind turbine rather than horizontal axis wind turbine. Okay, because whichever needs service, all is just on the bottom as a ground floor. Okay, and because there is no tower, okay, you can see horizontal we have a very tall tower to support the nutshell, which consists of gearbox and generator. But this one, because all the heavy part is located at the ground, it theoretically will use less material. You don't need to build the tower. The tower will already cost you maybe 20% of the total cost. So if you can save the tower, then actually you can save the cost and material. Okay, and it will be less noise from the standard turbine. Okay, and then another thing is it can use at the low wind speed condition. Okay, so you can mount it to the closer to the ground, but it's still not widely used because of the disadvantage. So first, you install the blade on the ground. What happened? Normally, why we want to install the blade on a very, very high location? Because we do not want something to block the blade. So if you build the turbine close to the ground, it means that you will have the less wind speed or poorer wind speed. Okay, this is the first disadvantage you build on the ground, but it's not the main disadvantage. Second disadvantage is about the force, centrifugal force blade. Okay, what's mean by centrifugal force? Okay, let's say I have the mass. Okay, and this is a point of rotation, and I rotate it. Okay, omega. So that there is always one force that the ball want to fly outward. Okay, because of the string holding it, so it will maintain as the line. Okay, this point we call as the centrifugal force. It will pointed outward. So let's say I have no this, I cut off the string. Of course, the ball will go out. Okay, so this one we call as the centrifugal force of the rotation. Okay, same thing happens here. If you look on the horizontal axis, when the blade rotates, what happened to the centrifugal force? It will move to this direction. Correct? It will point outward, the mass will point outward. So something like you just pull on the blade. So the blade will be subject to a tension force. And normally the tension force is okay. What I say that how you want to break a ruler? For example, you have a ruler, you want to break it. You want to pull to break it easier, or you want to bend to break it is easier. Of course, you want to bend is easier. So the bending stress and the tensile stress is totally different. The allowable tensile strength and allowable bending stress is different. Okay, you want to break a ruler, you bend it much easier than you pull it until it break. Okay, so same thing happened here. This blade is just pulled by the centrifugal force, so it's quite strong. But this one, mass over here, so when rotate, pointing outward. So actually, it break the bending to the blade, bending stress to the blade, and this actually will change. But this one you just pull on the blade. Um, it has very poor self-starting capability. Why? Okay, look on this. This is the blade, and you already designed the aerofoil shape, and you already predefine the angle of attack. Okay, so that when the wind hit on the blade, it will automatically rotate because you already create the pressure difference. But this one, you can see at different location of the blade. Okay, it will have different angle of attack. So that you need to move until a certain location, then it's only able to create the lift force by the wind. Okay, it's a good advantage, you can accept in all the direction, accept wind from all the direction, but bad is at the starting point. You need to make sure that the wind hit on the correct direction. Okay, but once it start rotate, then okay, because the blade will pass through the direction of the wind and create the lift force when it passes through the location. Okay, so for this case, you have very poor self-starting capability for this vertical axis wind turbine. So you need to give maybe an initial rotation to let it start rotating. Okay, so this is a problem of this turbine. Okay, so you can see that, as I said, when the blade go to the certain location where you will create the enough lift force, you will generate wind energy. You will generate electricity only at certain location. So it means that maybe only 1 to 2 times you will pass through every round. So it's not continuously capture the energy from the wind. But this one, for the horizontal axis, the wind turbine blade is keep facing the direction of the wind. So that I can say that it will continuously capture the energy from the wind because the angle of attack always the correct angle of attack. Not like this, it keep rotating. Sometimes correct, sometimes not correct, sometimes correct, sometimes not correct. Okay, so that the efficiency of this is much lower than the efficiency of this. Okay, so this is the main problem as well. And then you can see that this support at the bottom and then wind speed hit on this. So I need a support on the top. Okay, I need a support of the top of the turbine. So I use wire to hold the turbine. Okay. And I think that's all about the disadvantage. And the disadvantage is more critical than the advantage come from this vertical axis wind turbine. So we can see that most of the case we have horizontal axis wind turbine. So after this slide, all the discussion will be about the horizontal axis wind turbine. Vertical axis wind turbine, just for understanding that we have this kind of the wind turbine system. Okay. And this is the overall comparison between advantage and disadvantages for the vertical axis wind turbine. You can see that it is not suitable to use in the area of high wind speed. Then what's the point? Normally, we try to choose a location with a high wind speed so that we can get high power output. But this is not suitable for high wind speed location. So as I said, it's only limited usage. Okay, for example, in Malaysia, which we have low wind speed. Okay, and overall, you have very poor performance because of, as I say, it's not always face to the direction of wind. You keep rotating, but just hit the wind at the correct angle attack once a rotation. So of course, you will have a poor performance and reliability. Okay. Now looks on this horizontal axis wind turbine. Okay, most wind turbine generating electricity today are horizontal axis wind turbine, and it's predominantly medium-sized enterprise that have pushed wind market development. So let's look on the component of the horizontal axis wind turbine. Okay, maybe we start from the front. Front, we have the blade. Okay, and the blade is held by this rotor. All the blades are held by this rotor. Okay, and if you have the pitch control system, Pitch control is to rotate the blade, so that it keep facing, not facing direction, but you have the correct angle of attack. Okay. And then you can see that we have a brake. Brake is used when the wind speed is too low or the wind speed is too high, but not to slow down the wind speed. Sorry, not to slow down the turbine speed, but to stop it. Okay, when it's below the cut-in speed, we use the brake. Above the cut-out speed, we apply the brake. Okay, and then we have the low-speed stuff. Okay, so you can see that we connect the rotational of the rotor to the gearbox, because again we need the high rotational speed to generate power on the generator. So this is our gearbox, and not only the sound is come from gearbox and the blade, mainly it's gearbox lah. Okay, and then after the gearbox we have the generator, which we can generate the AC current directly. Okay, and then we also have the high speed stuff. Okay, nutshell is just a casing to cover the entire turbine system. And here is the controller. Controller is where we obtain the information of the wind speed and the wind direction. It's very important because remember that we need to change the angle of the blade accordingly to the wind speed. And we need to change the angle of the rotor accordingly to the wind direction. You must keep facing to the direction of the wind. Okay. So controller here we have two sensors, anemometer, which you have 3 cup over here just to measure the wind speed. Okay, and then we have vane over here, wind vane, which to indicate the direction. How is work over here? The wind vane is very simple system. It do not have very complicated sensor. It's just something, a piece of paper or a plastic. Okay, in any shape. Okay, so these pieces of plastic, it will always keep at a minimum resistance to the wind. Okay, so when the wind come, it will keep facing the wind. Okay, so they will create the minimum resistance. Let's say wind come from the front, but the wind vane is at this side. Okay, immediately the wind will move the blade, will move the wind vane to the back because it will blocking the wind. So it will move to the certain point that blocking is the minimum. So based on this controller will know where is the direction of the wind. Okay, this is a function of the wind vane. Okay, and next is the yaw control, yaw drive and yaw motor. This is to move the entire rotor to face to the direction of the wind. Once you receive the information from the controller, then you will move accordingly where is the direction of the wind. But of course, this will consume quite a lot of power. So that when the wind speed is too low, they won't move this and they will apply the brake. Okay, to make sure that it won't consume power. This is what the main part of the HAWT, horizontal axis wind turbine. Okay, any question until this one? Can follow on. Then we talk about number of blades. How many number of blades is good? You can use many so that high solidity, which is good for pump. You can use 1 or 2 or 3, which is low solidity, which can rotate very fast and give you very high speed. Very high speed is mean that it's good for power generation. But as I said, when the number of blades getting lesser, you should have the lower solidity and you should have the higher speed. For example, 1 blade. 1 blade should rotate faster than 2 blades. And 2 blades should be should rotate faster than 3 blades. So in that case, why don't I just use 1 blade? I use 1 blade, I can increase the speed of the rotation then I can smaller the ratio of the gearbox. Okay, I can use a smaller gearbox because the conversion will be lesser. Previously, maybe 3 blade is from 60 to 1008. Maybe this one is 120 to 1008. Okay, so the gear ratio is much lesser. Okay, but why we don't use this? But if you see this, yes, can you are correct. How to balance with one blade? Then two blade balance. Two blade really balance what? Why I cannot use two blade? I need to use 3 blade. Okay, so one blade definitely out already because you know it cannot balance. You want to make it balance, you need a counterweight. Okay, because you have the centrifugal force. Okay, let's discuss one by one. We start from one blade. This is a one blade system. And you can see that when you rotate, this is the center of mass, center of gravity. You will have the centrifugal force pointing upward. So it will create a very strong vibration because the centrifugal force keep changing the direction. Now it face to this, later it face to this, later it face to this and here. So it keep rotating, it keep changing the direction. See something like the unbalanced mass in the system. Okay, so eventually you need to add a counterweight which same weight as the blade, so that you have the centrifugal force to the left and you also have the centrifugal force to the right at the same time, so that both of them can cancel out each other. But the question is, if you want to put the weight over there, why don't you just put two blades, which will give you more lift force? One blade will give you a certain lift force. You give two blades, it should have more lift force. Why don't I just put another blade? Okay, so you can see the rotor must move more rapidly to capture the same amount of wind. Okay, and once you move faster, the sound you generate will be stronger. Okay, gearbox ratio reduced. This is a good part about one blade. You don't need to use a very big gear ratio. Added weight for counterbalance neglects some benefit of lighter design. You put one blade because you want to have the lighter design and a simple design, but now you need to add a counterweight. Okay, higher speed means more noise and visual and wildlife impact. Okay, when you rotate faster, you will kill more bird in general. Okay, so it will be more dangerous lah. And then blades easily to install because entire rotor can be assembly on the ground. You can see that entire rotor and the blade I can install in the factory and send to the site. But 3 blade definitely cannot. You can see 3 blade. How are you going to install and then hold by the lorry, send by the lorry to the ground? Cannot. Definitely you cannot install 3 blade and then send to the factory, send to the site. Okay, but 1 blade definitely okay. It will be very long, but it's not wide. At least the road still can support. Okay, so you can fit into the normal road. And this system capture less percent, 10% less energy than 2 blade design. Okay, and ultimately provide no cost saving. So this system definitely out. You get less output, but not very cost saving. Okay, and this one is a 2 blade design, 2 blade HAWT. Advantage and disadvantage similar to 1 blade. Okay, now previously we put a weight over here, but now we substitute it. Okay, sorry, maybe okay, never mind, continue. Previously I need to answer the phone. Okay, give me a minute. Okay, maybe you take a 5 minute short break and then we come back again later. Okay, let's continue on this two blade design. Two blade. Okay. So advantage and disadvantage is similar to the one blade. Oh, you can hear me, huh?
Can.
Okay, good. Okay, it's similar to one blade, advantage and disadvantages, and it captures 5% less energy than three blade design. Okay, so it means that two blade is better than one blade, but it's still less than three blade. Okay, advantage and disadvantage is still the same. Now we do not need a counterweight, but we put another blade. But you look on the second point. It's need the tearing hubs and a shock absorber because of gyroscopic imbalance. This is a new part. Huh? Is this balance? It's rotating? Yes. The centrifugal force cancel each other? Yes, it's balanced. Okay. But why I say you have another one called gyroscopic imbalance? In terms of the blade mass rotational, it is balanced. But in terms of gyroscopic means that now you want to rotate in two directions. Okay, the blade rotate one direction, and the rotor and the hub rotate another direction. Remember that we have the yaw control. Okay, yaw control. So the rotor must face to the direction of the wind, so it will rotate. So the blade rotate, the rotor rotate in two perpendicular direction. This is why we call it gyroscopic. Okay, and try to imagine in this way. When two direction of rotational rotate at the same time. Okay, so it means that sometimes the blade is horizontal. Sometimes the blade is vertical, correct? When you want to rotate to face the direction of it. Okay, so when the blade is horizontal, you will have what? Angular momentum. Okay, you will have the much higher angular momentum than the blade at this location. You will have the low angular momentum. And how to explain this? You can think about this. A lot of conservation of angular momentum. Okay, so if you open your hand, something like the blade is at the both side, then you will have very high angular momentum. Okay, so you have very high moment of inertia, and you will have a very low speed of rotation. And when you close your hand, something like this, similar to the when you put the blade up and down. Okay, your moment of inertia decrease, and your angular momentum increase. This one we call as a law of conservation of momentum. So we look on the inertia. Inertia in the layman term we call it as a resistance to rotate. Okay, so I can say that rotation of rotate high, resistance of rotate low. So that when the wind turbine blade is rotating, keep rotating. The resistance of rotation sometimes high, sometimes low. Okay, high, low, high, low, high, low. So what happened? You will create the strong vibration. That's why we call it as a gyroscopic imbalance. Okay, it's happened in the one blade as well. Okay, one blade and two blade also have this problem of gyroscopic imbalance. But one blade another imbalance of the rotation. One blade have two type of imbalance. Two blade have one type of imbalance. So that you need to give a very good shock absorber to the system to protect it. So in other words, you also need more maintenance when you have strong vibration. Okay, so that two blade system still out, we use three blade. Okay, once you have three blade, now we have the balance of gyroscope force. So you can see if you cut in the middle, okay, one blade and two blade. And the mass center of gravity of these two mass is closer to the middle of rotation. And which have one blade normally is far from the middle of rotation. So actually the gyroscopic also balance. The rotation, balance, gyroscopic, balance. So three blade is the best. Of course, three blade, four blade, five blade, or you can make the gyroscopic balance. Minimum three blade to make gyroscopic balance. Okay, so 3-blade you will have the slower rotation than the 1 or 2-blade, and it increase the gearbox and transmission cost compared to 1 and 2-blade, but it will be more efficient. Okay, as you see for 2-blade, it capture 5% less energy than 3-blade, and it look better, less noise because it moves slower, fewer but straight because it moves slower. Okay, so 3-blade is the best. Remember that what's the condition that we want? We want very high speed. We want we don't want any unbalanced force. Okay, so if I use 1-blade, 2-blade, it's not balanced. So I use 3-blade, good. 4-blade, also good. But 4-blade, you will increase the solidity of the system. Then you will change to high torque rather than high rotation speed, which is no longer suitable for power generation. Okay, and according to the study, 3-blade and 4-blade, 5-blade theoretically generate the same amount of power. Okay, not that you add 4-blade, you will get more. Yes, you add 4-blade, supposedly you will get more lift force because you have 4-blade absorbing the lift force from the wind. But at the same time, because of you have more blade, some of the time your blade will reach the turbulent flow location earlier. So to make the efficiency will drop. But again, you need to add extra material. You use more blade, you use more material. Okay, so to achieve this condition, I need balance. I need high speed. Okay, I need to save material. Then 3-blade is the best. So you can see that all power generation blade, apart wind energy, wind turbine is using 3-blade only, not 4-blade, not 5-blade, not 1-blade, and or 2-blade. Okay, so 3-blade is the best. Okay, another question: what is the color of the wind turbine? Anyone? If you look on the photo, or what's the color of the wind turbine? And then why? Why? You can see that all wind turbine is actually in white color. Why don't you make it in a very fancy color, red lah or black lah or whatever? These two reasons why we have to use white. First, we do not want it to absorb heat. Okay, because when the color become darker, so you will absorb more heat. Okay, so you will increase the heat, you will increase the friction. So we do not want it to increase any heat in the system. So we use white. Secondly is one need to make it visible. Okay, visible for maybe helicopter. If you make it black, maybe at night they cannot see it. Okay, so white is the best. But if you use a maybe fancy color like very shining yellow or green, I think it will create another problem. Okay, maybe something like you will be something like a light from the maybe signal tower for the airplane, something like this airplane. Okay, so that all the wind turbine is actually white. Okay, commercial one. First is to reduce the heat. Second is to make it visible by others. Okay, then then we talk about the design of the wind turbine. Then how actually we design. So these are design wind turbine. We talk about wind speed range. The design tip speed ratio depends closely on the number of rotor with blades. The maximum power coefficient of the 3-blade rotor is reached at the tip speed ratio between 7 and 8. Whereas for 2-blade rotor figure is 10, and for 1-blade it's about 15. However, this value can vary depending on the system design. The optimum tip speed ratio also defined as the design wind speed, along with the rotor radius of the rotation speed and rotor. So this equation is help you to define what is the design wind speed. Okay, at the design wind speed, you should get the optimum efficiency or maximum efficiency. Okay, so you have to choose wisely lah. At which point you want to have the maximum efficiency. So based on the optimum tip speed ratio, you design the design wind speed. Okay, but normally we have to, based on the location, you need to have the history of the wind flow. Okay, and then you only set your design wind speed. So based on the design wind speed, you know that what optimum wind speed that you need. Sorry, optimum tip speed ratio that you need, and then you can find whichever wind turbine actually meet your requirement. Okay, and you look on this 2 pi Rn on the top. It's actually referred to the rotational speed of the rotor. Okay, and this one is normally we are not much able to change this because of you need to get the proper rotational speed for the power generation at 60 hertz. You want to generate the AC current at 60 hertz, so that you need to proper design this. So normally we will control on this blah blah, which is the optimum tip speed ratio. Okay, so if you look here, for example, the optimum tip speed ratio of the 3-blade turbine with rotor radius of, you can see the radius of rotor is 22 meter. One blade length is 22 meter, and this is not the largest. And the rotational speed of N is equal to 28 RPM. Okay, and therefore the design wind speed is 8.6 meter per second square per second. Okay, so this is our design wind speed. So based on this turbine, the design wind speed is 8.6, which means that at 8.6 meter per second, this wind turbine will have the maximum efficiency. And then based on this 8.6 meter per second, you have to compare with the data from that location that you choose. Is that 8.6 good enough? For example, this one, I think 8.6 is not very good answer. Okay, you see that 8.6 is around here already. Okay, so I would say that that is too fast, because quite rare the wind will happen at 8.6 meter per second. So normally the design wind speed will set at where there's a high frequency to happen. Okay, maybe around 3. I think this is the wind speed graph for Malaysia lah. Okay, you can see that mostly at around 3. So the design wind speed should be around this value. If you want to find the wind, you want to build a wind power in Malaysia. Okay, 8.6 is definitely too high for this location. Okay, but of course, as I said, that rated power will be more important than the design power. Okay, at design wind speed, your system will have the maximum efficiency. At the rated power or rated wind speed, your system will have the maximum output. So maximum output important or maximum efficiency important? Okay, so definitely is maximum output is important, because why efficiency is important? When the input is very costly. Okay, for example, I use phosphate fish. Okay, then the efficiency will be very important, because if my efficiency low, I need to use more input and it's very costly. But now wind and solar, both input is actually free. So when you take care of the free resources, efficiency is not an issue. Okay, but of course, if you can increase it, you also can get better lah. But we will look on the maximum power output. Okay, it will be more accurate. Okay, unless you can see the design wind speed is very important for wind turbine with constant speed. Okay, fine. If you want to target on a constant speed, then the design wind speed is very important. But most of the cases, we do not have any constant speed. It's always change from time to time. Okay, so let's look on this. The rated or nominal wind speed, Vn, of the wind turbine is usually different from design wind speed. At the nominal wind speed, the wind turbine generates the rated power. This is where you have the maximum output, rated power. Okay, and this point normally is not maximum efficiency. Okay, so as I explained previously, at very low wind speed, the operation of the wind turbine makes little sense. No power or only a very little power can be taken from the wind, and the wind generator can even become a power consumer. Okay, because you need to rotate the wind turbine to face to the direction of wind. Therefore, the rotor blade should stop the wind turbine below a predefined starting wind speed, or we call it as a cut-in wind speed. And then above the nominal wind speed, the power of the wind turbine must be limited. If the wind speed becomes too high, the wind power plant can be overloaded and damaged. Therefore, wind turbine must cut out at high wind speed, V out. Okay, we cut out. Okay, so this is a complete graph of the different type of wind speed. Okay, you can see when it starts to have the power, we call it the cut-in wind speed, where you start to rotate the turbine, which is between 2.5 to 4.5 meter per second. And then when you have the maximum efficiency, here you can see two lines. Okay, first curve, this one, follow my cursor. This line is referred to the efficiency, power coefficient. Okay, and another line is referred to the power output. Okay, so you can see that at the design wind speed is where you have the maximum efficiency. Maximum efficiency is over here. Okay, which around 8 meter per second wind speed. But do you notice the output? Output is very low. Although the efficiency is very high, but output very low. Because power is directly proportional to velocity cube of velocity. Okay, so after the design wind speed, then we go to the nominal wind speed, which at this point. Okay, where you have the maximum output. So which one important? You can see this one is a nominal wind speed, which will give you the power output of 500 kilowatt. And this one is the design wind speed, which is the highest efficiency, but just give you the power output of 150 kilowatt. Okay, of course, we take care of 500 kilowatt rather than 150 kilowatt. Okay, so design wind speed is not much important compared to the rated power. Okay, and then at 25 meter per second, we have the cut out wind speed. This is to protect the generator and gearbox from destroyed by the fast rotation of speed. Okay, so we cut off, we stop the wind turbine blade. Okay, so your output definitely will drop to zero. You can see that very sharp drop because you suddenly you stop the turbine to rotate. Okay, and then we have another one called survival wind speed. Survival wind speed is tested when the wind turbine is not rotating. Okay, so it means that at this above this wind speed, even you don't rotate the turbine will be destroyed by the wind. By the 50 to 70 meter per second is totally too high. The speed of the wind is totally too high. So it even can destroy your building, not say a wind turbine. Okay, so this is a survival wind speed. Okay, so operation of wind turbine actually quite complicated lah. So they're not like the solar energy. Photovoltaics, everyone, I can have the 1 or 2 years experience. I can set up my own company and I sell the solar panel system. Very easy to build as long as you know the process. Okay, to follow the regulation, then it should be okay. And then of course you need to have the cert for certified engineer. Okay, or certified professional engineer. Then it's definitely okay. You can build your own company and then you can do it. But this one, wind turbine, is not so simple. It's much complicated than the solar energy. Okay, so that only the huge company, multinational company, able to do that. Okay, normally conquered by the big company lah. Okay, so understand the curve. There's a 1 year question paper come out with it, ask you to draw out or sketch out the power distribution curve. Okay, so and label correctly. So you should be able to understand the concept. But of course, the value here is not very important. Just agak-agak you know the range is good enough. Okay, because different type of wind turbine, we have different value of this. Okay, so that is value is not need to be exact, but the shape is definitely all the same. Okay. Okay, so this is about the wind speed, and then we talk about yaw wing. Yaw wing we also have two types. Yaw wing is mean that we move the wind rotor to face to direction of wind. Okay, so we also have passive yaw wing or active yaw wing. Passive yaw wing is mean that we don't need energy input. It will rotate to face the wind itself. But active yaw wing is mean that we need to rotate the blade to face to direction of wind. Okay. So yawing refers to the circular motion of the axis of the turbine in the plane of the bed. Horizontal axis wind turbine must always follow the direction of the wind in contrast to the vertical axis wind turbine. Remember that I told you? Vertical axis wind turbine can accept wind from any direction, but this horizontal wind axis, it always faces to one direction only. So to capture the wind energy, you must make sure that it facing to the direction of the wind. The orientation of the rotor blade must be chosen so that the rotor blade faces the wind at the optimum angle, which refers to the angle of attack. You need very high lift force, but you do not want any drag force. This is the ideal case. This can be a problem for pitch control wind turbine if direction of wind change very fast or is too steep. Hence, high power fluctuation can occur and must be cushioned by change in the rotor speed. Okay, so look at here. We have the active and passive yawing. And most of the commercial scale wind turbine using active yawing. The reason is the turbine is actually too big. So you must use energy to rotate it. Okay, so active yawing, you can see all medium, large turbine produced today. Some small turbine from European are using active yaw. Okay, so first you have the anemometer to measure the wind speed and the direction. Okay, so you will send a signal to the yaw drive. Where is it? Okay, you get the signal from the controller anemometer, and you will send a signal to the yaw drive, and yaw drive will rotate accordingly to the direction of the wind. And of course, this yaw they need motor. Okay, so you need the power. So this one we call it as a active yawing. Okay, very direct forward. You get the reading from the controller from wind vane and anemometer and rotate accordingly. This one active yaw. Then passive yaw is normally used for the small wind turbine. Okay, how you want to make, okay, for example, this one, passive yaw. How you want to make the turbine keep facing to the direction of the wind? Very easy. You put a vane at the back, and the vane will always align to the direction of the wind, because it will move to the location which has the minimum resistance. Okay, the vane, you see the vane at the back, the tail at the back. In order to reduce the resistance, it will always align with the direction of the wind, so that the wind turbine blade will align with the direction of the speed as well. So we call it as a passive yaw. It rotates its own. We no need to give any motor control. But this fan is not able to control the heavy commercial use wind turbine. Only for the small turbine, you can use this kind of fan. Okay? The concept is very simple. So you can use fan to rotate, or you have to use motor to rotate when it's too heavy. Okay. Another thing is about the upwind and downwind turbine. Okay. First is about the definition. Upwind, you see, the wind will hit on the blade first before the nutshell. Okay, the casing at the back. Downwind is the wind have to go through the nutshell before hit on the blade. Okay, but if you see which hour in the market, definitely everything is upwind rotor. Okay, where the wind will pass through the blade first and only reach the nutshell. The reason is this nutshell, this is a shape. Okay, so when the wind hit on something object, it will create the turbulent flow at this area. Okay, so in other words, it will reduce the efficiency of the system. Okay, can you see that? Because it hit on this thing, hit on some object and nutshell, so it will create the turbulent flow. So this turbulent flow will reduce the efficiency of the turbine blade. Okay, but good thing of this is front part is nutshell, back side is the blade, so that this turbine can automatically face to the wind. You do not need active control. Okay, because the blade, if you can imagine, when the wind comes, definitely the blade will go to the back. If the blade is lightweight, it will automatically go to the back. You don't need to face the direction. You will always face to the back. Okay, this is the nature of it. You will push away whatever have high resistance to the back. Okay, now of course the blade have the higher resistance than the nutshell, so push the back. Okay, but this upwind rotor, yes, you will have the higher efficiency, but automatically if you don't hold it tight, the blade will rotate to the back. Okay, so this is the advantage and this is the advantage of turbine. But of course, upwind turbine is widely used, so it means that it's much better in terms of overall efficiency. So if you read from here, upwind turbine, the position of the rotor relative to the tower is before the tower in the direction of wind. No shelter zone by tower. Okay, this is shelter zone created by this nutshell and tower. We call it shelter zone, which create the tubular flow. And active yaw is needed because without the yaw, the blade definitely will move to the back. Okay. Then for downstream turbine, the position of the rotor relative to the tower is after the tower in the direction of the wind. And the rotor is that the rotor blade have to continuously pass the shelter zone of the tower. This produce high mechanical strain and noise emission due to turbulence from the tower and the nutshell. But good thing is the wind pressure adjusts rotating blade optimal to the wind, automatically to the wind. So it will change, optimize the direction automatically. You don't need to do anything. Okay, this we call it upwind and downwind. And whichever you see the most, definitely is the better design. Okay, we always, because our wind turbine system is actually quite matured already. So you can see that entire market use a similar design. You can see solar, wind, hydro, all of them use a similar design because it's very mature technology. But if you look on the wave or tide, what happened? This is the many type of design. No one able to fix one type of design which have the advantage over the rest. Okay, so different companies they use this totally different design for wave and tide. We still not able to get one method which is very efficient in conversion of the energy for wave and tide. Okay, so this is the percent of cost share of the 5 megawatt turbine component. So you can see tower contribute 26% of the total cost. So if you can save, you can no need to build the tower, then you save 26% of the cost. And the tower is about 40-meter height. Okay, maybe around 15 floor or the 15 floor, yeah. And up to more than 100 meter. I'll try to imagine that a tower with 100 meter. Okay, I think one floor is just around 3 meters, so 100 meters is around the 30 floor of the building. Okay, 30 level. So actually it's very tall. And rotor blade 22.2%, and the length can be up to 60 meter. One blade is 60 meter long. And then I think these two already contribute about half of the total cost, tower and the rotor blade. Okay, and then rotor hub 1.37, bearing 1.22, and main shaft 1.2, 1.9, and main flame 2.8. So we look at this side, gearbox, another third costly part is actually gearbox. Okay, 12.9% of the total cost. And this power conversion, transformer, okay, transformer to increase the voltage so that it can be used for long distance transmission, okay, with less losses. And we have brake system 1.3 and nutshell housing 1.35. Okay, this is share of a 5 megawatt turbine component. So if you really want to reduce the cost, then you can think about these three: tower, rotor blade, and gearbox. So normally, if you use one blade or two blade, I think you can save a little bit on your gearbox. Okay. And these are a little bit about future technology development. Okay. Improvement performance, maybe I can improve the capacity. How I improve the capacity? First, I increase the height. So when you increase the height, supposedly you will increase the wind speed. Okay, as we know, when you go higher, the wind speed is higher. Nothing block the wind. It will flow faster. Okay, and maybe you can use a larger blade. Okay, which create a better lift force. And we can use a semiconductor, conductor, conducting magnet. This is about inside the generator. Remember that how we create the current from rotational. You need to cut through the magnetic field. Okay, so if your magnetic field is generated by a superconducting magnet, so it means that you have stronger magnetic field. So for each of the cut, you will generate more current. Okay, so in case we can have the superconducting material, then our generator will be more powerful. Okay, so this is a possible improvement. And we also can improve the capacity factor. Okay, so that we have the more consistent wind, which we can build at a higher height. And we can use the advanced control method, which is an individual pitch and smart blade. Okay, how they want to make the blade smart, I don't know. Okay, but individual pitch, I think three of the blade, they have their own angle. Okay, and then maybe site specific design. Different location, we may have the different condition. Okay, maybe some of the location, the wind speed always come from same direction. Some of the location, it keep changing. Some of the location, you have the hurricane. How you want to absorb the most of the wind. Okay, so this is something that we can improve, or we can reduce the cost. We can reduce the weight, right, to the design, but seem like it's out already. Okay, advanced material, for example, composite. I know that a lot of researchers study on the composite. I want to try to reduce the weight of the blade. I think now they are using fiberglass, or maybe the other type of composite, which lightweight and very strong. Okay, similar to the material used in the aircraft. Okay, and maybe we can find a better composite in the future. Then we can reduce the weight. Of course, we can reduce the cost and increase the efficiency. And direct drive system. Direct drive system is mean that I do not need a gearbox. But the problem here is because it rotates too fast. It will create noise and it will kill the bird. Okay, so and then when you rotate fast, it means that your maintenance cost, the strength of the blade must be better. Okay, so everything is just ideal case lah. How to improve? We still have faced a lot of problem on achieving this, and you can build it offshore, but the problem is about the foundation and construction and maintenance. Foundation very difficult to build, okay, because you want to make it floating on the sea, or maybe foundation on the seabed. And then maintenance, because of the sea water is very corrosive, so it's another big maintenance of the system. Okay, so before that, I remember that I see, okay, let me show you only one video. Okay, have a look on this future of the wind turbine. Maybe you can have a look on this. The sound is just a music, so I turn off the sound. So have a look on this. Which one is possible to happen in the future? Okay, so first one is the buoyant air turbine. So we know that air wind speed will be stronger at a higher altitude. Okay, but to build the tower is very expensive. Now we already built up to 100-meter height. Okay, what if I can make the turbine floating on in the air? Maybe just fixed by maybe a cable or wire, just holding it. It won't carry away by the wind. Okay, it's a good idea, possible to happen, I guess. Okay. These are design, okay. Carry wind speed increase in altitude from sea level. So this one should be provide better opportunity to tap into high speed, high quality wind. But the problem is how you want to fix the wind turbine. Okay, because it's a floating, and the wind turbine system is heavy. How you want to make it floating in the air? Okay, and the support also is an issue. But possible to happen now, of course. Second, Okay, this one okay lah, floating on the sea, but quite general. Okay, this one is make use of venturi effect to accelerate the wind past the turbine, something like a binary lah. Okay, so when you can see that they make it. Okay, there's a curve when you go into the turbine blade. So that curve, you increase the wind speed. You make a curve for it to flow, something like aerofoil shape lah. Okay, so the wind will flow faster. Okay, so you use this method to increase the wind speed. But of course, in general, it's actually focus all the wind to one point. Okay, because you still remember that conservation of energy. You are not able to break the rules, conservation of energy. So in ideal case, we still can consider it as we focus all the subpoint, all the subwind into one point. This one, one tower for many rotor, possible I guess, but very ugly lah, of course. Okay, I think that's all about future of the wind turbine, maybe future development. Let's continue with our slide. Oh yeah, they have this. Okay, other than that, we still have the improving reliability and availability. We are using a more advanced forecasting tools so that you can choose the proper location. Okay, and maybe adjust the store control accordingly. Okay, and then we can deal with the system load such as the advanced control method, material, preemptive diagnostic, and maintenance. So this one is about all the control method lah. Maybe you can expose in this in student. And we can use a direct drive, complete removal gearbox. This one is a good idea, but we still face a lot of problem of the strength of the blade. Okay, and novel designs, you have showed that floating direct drive and high altitude concept still possible, and sky wind power. Okay, these are all the idea about future development. Okay, I think we have done the theory part. Okay, so now we go a little bit, maybe we try example 4.3, last example before we dismiss. This is extracted from the past year question. A small horizontal axis wind turbine of 12 meter diameter has a cut-in wind speed of 4 meter per second and cut-out wind speed of 25 meter per second. And the wind speed over 12.5 meter per second, the wind turbine operates at its rated power. At wind speed below this, the turbine operates at variable speed. Maximum power point tracking. The aerodynamic, okay, the state at maximum power point tracking means that it always generates maximum possible power. Okay, because if you don't have the maximum power point tracking, the power output will definitely depends on the load that you give to the system. Okay, like remember the solar power system, you adjust the real state where you adjust the IV curve. Okay, the aerodynamic power coefficient of the turbine is Cp equal to 0.4, and the electrical conversion efficiency of turbine is 75%. The density of the air is 1.2 kg per cube meter. The wind turbine operates at the start when with the following characteristic. Okay, so instead of giving you the probability, this question more direct forward. It gives you the hour. So in 1 year, you have the wind speed of 2 meter per second for 1049 hour and 4 meter per second for 1916 hour. Okay, this is similar to probability density function, but now give you in terms of actual value. So what is the question? Calculate the rated power of the turbine. Maybe you try first before we discuss. If you okay, then let's continue with this rated power. So rated power is mean that the maximum power of the system. So you refer to the question. Which is the rated power? Okay, at wind speed of 12.5, the wind turbine operate at its rated power. So it means that rated power is at wind speed of 12.5. Okay, so P rate. What's the equation for wind energy? 1/2 rho A V Q. Okay, and now because of this type of wind turbine operate at the rated power of 12.5, so you should be able to get the rated power over here. Okay, the density of the air 1.2, the rho, and then A is the strap area. So you're given the diameter of the rotor of the blade, then you should be able to get. Okay, maybe we calculate the wind power first, because turbine power has to consider the efficiency as well. But now we calculate what energy content in the wind. 1/2 rho. A is 12-meter diameter, so pi r squared. Okay, pi 6 squared. Okay, VQ. V is the velocity, so just now we get 12.5 Q. Give me your answer. Okay, 132.54. But remember, this is just the power of the wind. Okay, so you want to calculate the rated power. So we have to calculate based on the power of the wind. So what are the efficiency that given? Power coefficient 0.4. Okay, so it means that only 0.4 of the total wind energy will be absorbed by the turbine. Okay, and then now after you absorb again, not 100% will be converted to electricity. Okay, only 75% will be converted to efficiency. Okay, 100% of the wind energy hit on the wind turbine blade. Only 40% of the wind energy captured by the wind turbine blade. Okay, once it captured by the wind turbine blade, it need to use the energy to generate electricity, do the conversion, okay, using the generator, and the efficiency is 75%. So you have to consider both. Okay, so should be times CP times electrical efficiency. So I have 132.54. CP is 0.4. So I left only 39.76 kilowatt. And this is the rated power of the system. Okay. Then the second question. Calculate the maximum power and the annual energy yield at the wind speed of 10 meter. At wind speed of 10 meter, you want to calculate the maximum power and annual energy yield. Okay, so this is the wind speed of 10 meter. So maximum power, I think very direct forward. Okay, P 10 because wind speed 10. So it should be PV, which is 1 over 2 rho AVQ times efficiency, power capacity. The power capacity, we call it CP, power coefficient, and multiply with the conversion of 75. So you get the power at the wind speed of 10 meter per second. Twenty point 2636. Okay, so maximum power done. Then the energy yield. What is the total energy yield for the system at 10 meter per second? Okay, so the power is 20.36. and the time you have is 1082 hour. Okay, so power, time, you should get the annual energy U. Okay, power is 20.36 kilowatt. And the times I have is how many hour? 1082 hour. So it means that I can get 22.03 megawatt hour of energy for 1 year at this speed. Yes, okay. Then the last one, you calculate your own. If the energy NEU is 84.7 megawatt hour, calculate the capacity factor of the wind turbine. So capacity factor is the actual power divided by the maximum power or rated power. It can be power, okay, it can give you in terms of power, actual power divided by rated power, or maybe actual energy U divided by the rated energy U. Okay, so for this case, actual is given already 84.7. But maximum is not given. But I know that the rated power is 39.76. Okay, so if I run it for 24 hours a day and 365 days a year, okay, times 24 times 365. Then it represents the rated energy U for 1 year. Okay, so it means that we operate at the same power output, at the rated power output for the whole day, whole night. Okay, for 1 year. Oh, Samuel, you round up too much already. 0.25 still okay lah. But don't round out too much. 0.2 is over already. Okay, so capacity factor for this system is only 25% or 0.25. Okay, any question until this point? No question, can follow. If no question, then I think we can dismiss now. Okay, and see you again next week. Okay. Okay.
Thank you, sir.
Yes. Okay. No question. Good. Then.